Greetings. I welcome you all to the new lecture of this course, wherein now we will be discussing on the pyrometallurgical processes of WPCB recycling. Now, we had very recently discussed the importance of pre-treatment and how ECs are to be removed from the WPCBs, and we've also discussed the delamination. Now, it becomes very important that after delamination, we must have a very well defined route for recycling the PCBs. One of the ways that by default we can just think of is basically we go into the pyrometallurgical process. Suppose that we have a large stock of WPCBs that we can easily recycle. Now, that stock can be directly charged in a suitable furnace, and we can go ahead for the pyrolysis or let us say metal recovery. Now, one of the ways that one should be thinking of for metal recovery is that we can do it in the conventional way, or we can have some other modifications during the process, so that we are able to tap out maximum from the pyrometallurgical operations that we do. Now, there are many variations to pyrometallurgical operations. Some of the furnaces can be rotated. Some of the environments that are present inside the furnaces can be controlled. So, inert atmosphere or not inert atmosphere. What is the process parameter for a given furnace that governs what is going to be the end result of the pyrolysis operation. Now, we can have extensive discussions on many operations that have been explored and are being implemented at different levels, but presently we are going to concentrate on some of the processes that generate in general good output. And of course, it is fair enough to assume that in case we are going for conventional processes, we can end up with metal master alloys. Now, that may be a good product, but then after that we will have to go think about the refining of the master alloy and further separation of metals if we want to go into that route. And of course, there is the generation of slag, then the slag recycling and dust, the process dust that is generated, effluent dust, that has to be processed separately. So, metal extraction is a challenge, and the generation of slag is also a problem, which means one has to invest on these fronts as well. So, we are going to discuss pyrometallurgical processes that are oriented towards maximum metal recovery along with other materials as well. So, let us go. And we know that we have been discussing extensively on WPCB. So, the composition is already known to us. It is like 30 to 40% metal is present. We have nearly 30% of polymers, and we can have 30 to 40% of oxides, refractories basically. These are basically oxides, and we also know that nearly from a general perspective, we know that 3 to 7% of total e-waste is basically WPCB, which means it is a very big contribution given the gigantic quantity of e-waste that we are producing per year. And considering the case of India, we have this means this is the quantity 4,137,000 metric tons. So this is basically 1000 metric tons, and this value is very large, and this is just a very recent data. It's in 2022, and we are talking about India. So this is the e-waste generation in our country, and we know that WPCBs have lead, chromium, mercury, cadmium. Of course, these are present in smaller quantities, but nonetheless these are present, and these are hazardous. Therefore, recycling becomes so important. Directly charging it in a furnace may not be a very attractive option because of the generation of gases. We are looking at, just in the previous classes we had discussed that the epoxy resins are present, flame retardants are present. These are materials that lead to the generation of hazardous gases, and if these gases are coming in contact with humans, then it can lead to lots of repercussions and health hazards. So one has to really think how we are going to go about the whole pyrolysis operation. What are the important pre-treatments? Important pre-treatments specifically for pyrometallurgical operations. In such a case, we can go for crushing or shredding. Of course, why are we doing this? Because we want to reduce the particle size. Then we can have screens. Again, why? We wish to have separation of particles on basis of size and shapes. Then we have magnetic properties. We are using what? We are using magnetic separators. Or drum separators. And then we have electrostatic separators, electrostatic properties. So we know that we are going to have eddy current separators. Similarly, following that, we have density separations. So we can have fluidized bed, or cyclones, hydrocyclones. And finally, we can have surface properties. So we go for froth flotation. So when we have such long chain of important pre-treatments, it's not necessary. It just adds to the quality of feed. So one can totally bypass these types of operations, and one can just directly charge the PCB assembly even without delamination into a furnace. That will do what? That will just lead to the melting of all of the components. We have, let's say, appropriate temperatures, we have good slagging materials. Slagging materials means we have good fluxes. Just melt the whole PCB itself. We will generate lots of gases. The slag composition is going to be very complex because we are going to have many polymers and different materials coming into picture, and the product that we will get may not be of our desired composition. So removal of components and pre-treatment helps us to make the metal fraction more concentrated, more oriented. So the raw feed is of basically our own choice. We are able to design our raw feed for higher metal recovery. This means material control, material properties help in designing feed of the process, and this leads to what? Improved metal recovery. Now, what exactly are the types of pyrolysis? What are the types of pyrolysis operations? We have, and of course, pyrolysis operations means what are the operations in pyrometallurgy that have controlled atmosphere for good material recovery, because we don't want the hazardous gas to generate. Thermogravimetric analyzer, fixed bed reactor. Right now we are just describing different types of facilities that can help in the pyrolysis. We see that thermogravimetric analyzer has poor mixing. You can have good control over temperature, but you'll get poor mixing of products. Fluidized bed reactor is basically continuous operation, low operation cost, and poor temperature control. Then we have batch reactor. It gives us high efficiency, high labor, but it has high labor cost, because one has to remove the material and recharge the furnace. Then there is the problem of variation of batch to batch output. This is very crucial because we do not know what we are charging, and it becomes very difficult to really be very sure about what is the overall concentration that we will be getting from a single batch to the next batch. This is a very big of a challenge. So in microwave we know that electricity requirement is is important parameter, because it's not just heating, it's also providing the microwave input. We have good control, easy control, and good heat transfer. But the mass control is difficult to handle. So difficult mass control in the process. So we have different types of pyrolysis operations, and we see that for every reactor that we have, let's say fixed bed or a batch reactor, or we can have other heating mechanisms also, and we can have microwave, or we just go for a very controlled small experimental setup. Each reactor itself has its own advantages and disadvantages. What is it that we wish to optimize? It is dependent upon the reactor itself. So both batch reactor and continuous reactors can have their own nuances. One can have different types of advantages and disadvantages associated to them. Now we'll go ahead and see what are the important parameters. Pyrolysis process parameters. And we know that typically speaking we have 300 to 800 degrees Celsius. Of course, this temperature, outer temperature range can go to, as we had discussed in the previous class, it could go to up to around 1300 degrees Celsius, but generally speaking it can be up to 300 to 800 degrees Celsius. And this is the temperature range. And what exactly are we looking inside? So we have important chemical reactions. What are the chemical reactions that happen? So we have dehydration, debromination, and dehydrogenation. So dehydration and dehydrogenation both are present in the pyrolysis of WPCBs. And what really happens is basically smaller molecules are produced. Smaller molecules are produced, and it leads to generation of heterogeneous mixture. One just might wonder, what type of mixture are we talking of? This mixture, the composition of this mixture we really can't predict. It depends upon what we have fed, in what quantity, and what was the initial composition of whatever we have fed. And then we, let's say, operate it at given operation parameters, and then we get to see the output. This heterogeneous mixture is what we get after the pyrolysis. So gaseous products, the oil, pyrolysis oil and char, we separate that out, and there is this heterogeneous mixture which contains metal and other fractions. So we can't really pinpoint this is going to be the composition. It again depends upon the feed and how we processed it. So the heterogeneous mixture, which is basically having the metal, is produced with the gases and char. Of course, we are also considering oil inside. So gases, pyrolysis oil and char. What are the parameters? So this is what is general outline. This is basically the outline of operation. But what are the parameters? So when we look at parameters, we have temperature. Then we have power and heating rate. And then we have particle size. When we talk about temperature, generally speaking, high temperature, we know the temperature range itself. So high temperature generally means good reaction rate and decomposition of WPCBs. By decomposition of WPCB means we are going to get heterogeneous mixture, char, pyrolysis oil and gases. The changes in temperature does not affect the mass of residue, the heterogeneous mixture itself, much. It does not affect the mass of the residue much, but it provides, we should say promotes, not just provides, it provides an opportunity, promotes the conversion of volatile materials to volatiles or volatile materials to gases. So higher temperature can lead to this. It really doesn't affect the mass. Now, when we talk about power, we can have, let's say, microwave, if we are using microwave. So microwave power can lead to, if we are increasing this, we are basically leading to higher reaction rate, higher heating rate. And higher heating rate means everything is actually interconnected. Higher heating rate means early decomposition. It starts early, it ends early. And higher decomposition rate. So not just early, it becomes quicker. Finally, we have the particle size. Now, this is something that we can debate. Powdered particles. So suppose if somebody has used powdered PCB, it leads to higher gas generation. Whereas if the particle size is larger, which means coarser particles. Larger means coarser particles. So we can have higher pyrolysis oil generation, which means that it is not complete, which indirectly it means that we have to go for incomplete pyrolysis. So if we are using powdered particles, we have gas generation. We have larger particles, we can have oil generation. Now, what exactly is it that we wish to perform is totally dependent on what is the product that we wish to make. Do we want gas or do we want pyrolysis oil? What is it that we wish to generate and in what quantities? That will decide whether we want powdered particles or somewhat larger PCB particles. Now, there are some advanced processes also. Which we will be discussing. So, we have catalytic pyrolysis, wherein we are going to use catalysts. We have copyrolysis, wherein we can have different materials coming into picture along with the PCB itself, and then we have molten salt pyrolysis, wherein we are going to use molten salt. So, when we look out for catalytic pyrolysis, we have use of zeolites and metals and metal compounds, metals and metal oxides. So, it is zeolites and metals and metal oxides. So, what are the common examples? We can have MgO, CaO, and then ZSM5. ZSM5 is basically a zeolite, and then we can also have copper and iron. These are basically the catalysts that have been used for the pyrolysis. And then what are the properties that we get? So, we have generation of lower pyrolysis oil. We have reduction of time, pyrolysis time, and activation energy. So, it becomes easier. And then we have bromides converted to bromine and or hydrogen bromide. So, when we think of copyrolysis, it's a bit different. So, when we are using two or more materials for pyrolysis, it's called copyrolysis. So, we can have, let's say, use of Chinese fir sawdust or rice husk or red mud, and people have been exploring many different materials, so not just these. And if we are doing this with the WPCBs, we are going to get some different output. We have high quality, high value pyrolysis oil, which can be used as a fuel. So, but the bromine goes in char, bromine fraction in char. So, the char that is produced has the total bromine. Now, when we look at salts, so generally speaking, salt bath can have, of course, this is just a typical example that we are looking at, Li2CO3, Na2CO3 and K2CO3. So, it could be having all of equimolar concentration, so 33% each. If this bath is used, then we are we can also have an advantage of, let's say, bromine conversion, 99% bromine in salt bath, and basically it leads to alkaline bromine, alkaline metal bromides, and we have recovery of 95% copper. So metal recovery is also described. Now when we look at the overall in general PCB recycling, we must look at energy and material flows. These are very important, and it helps us in understanding how material is extracted when we go into pyrometallurgical route of recycling. A generalized diagram we are trying to draw here. So let us have WPCBs, and we had our operations. So we did pyrolysis, and we also had energy conversion. What we get is syngases, liquid products, and then we have solid residues. But these gases can be treated as fuels. So we have fuel, and this is basically energy usage. So one path is basically wherein we are just going from pyrolysis to gases, and then to gases to energy uses. If we are really not interested in that, then we can go for material path. So when we look at material path, we have liquid products, and liquid products basically means chemical materials. One has to, of course, purify it and get different types of output from it. And we also have solid residue. We'll now discuss what we are looking at when we think of material output. So separately we have solids, and then we have liquids. And again we are still discussing material flow. So we have metal fractions and we have non-metal fractions. And in liquids we have the liquid generated products, we have the chemical materials. We need to go for debromination, and of course the purification, and we get the final chemical products. And it follows a very good streamline that we are able to recover lots of products. Now in the case of solids, when we look at metal fraction and non-metal fractions, we have non-metal fractions is basically synthetic products, and metal fractions are basically one has to purify and get the overall output, final recovery. Now when we think of pyrolysis liquids, liquid oil, we get that this product isn't very good fuel for incinerations, and it means that one has to have many further facilities, because the presence of particulate matter in this output makes it difficult to use in a general, as a general fuel. So when we think of pyrolysis oil, we can get key components like phenol and isopropyl phenol. But the key challenge is generation of pollutants, which makes this whole process a bit of a typical health hazard kind of situation. So one has to think around these pyrolysis products if they wish to reutilize them as fuels. So we've seen that in this class that many processes are available in pyrometallurgy that give us wide range of alternatives and products, and of course one has to think about refining the final metal products to get the desired composition, and one has to go into other routes in combination with pyrometallurgy to get the final output. We'll discuss in the upcoming classes. Thank you.